the way I introduced the rate region was, the throughput region was that in every slot, there is a throughput region for that slot for two UEs, UE0 and UE1, for example. The orange throughput region could be in one slot and the blue in the other slot. And if there's half the time orange and half the time blue, then you would get this polygonal throughput region, which is of course very simple, just for illustration. Okay, now one of the things to take away from here is that, of course, first of all, for M UEs, there will be an M-dimensional region. This is two UEs, as a two-dimensional region. And for M UEs, there will be an M-dimensional region. One point to take away also is that if you look at this point, where the other UE is getting zero throughput, this UE can get 130, 100 plus 160 over 2, 130 Mbps on the average. Okay. Sometimes it gets more because the channel is good, 160. Sometimes it gets 100 and the channel is not so good for it. On the average, it can get up to 130. And any throughput below that, depending on the scheduler. Similarly, this UE, UE1, can get up to 120 when the blue triangular rate region is in operation. The channel state is blue. When the channel state is orange, it can get 60. On the average, you can get no more than 120 plus 160 over 2, which is 90. So this is that rate. Okay. So the orange rate region is the average rate region. UEs can get more or less in particular slots because of the channel variations over time. On the average, they will only get, this one will only get at most what that number indicates and at most what this number indicates. Why average is important? We'll see it a little later. Okay, averages are important because you're not dealing with the system for 10 seconds or 20 seconds. You're dealing with the system for a long time. And it is the average that will govern how much rate you can carry. If there's a video of 1.7 Mbps and the rate at which this network can serve the video is only 1 Mbps, the video will not go through. It may go through for a few slots, but then you will see a bad channel and then the queue will build up. Again, you will see a good channel. The queue will drain slightly and then you see a bad channel. On the average, you will see no more than 1 Mbps. So the throughput will keep on building, the video will keep on building up. If it's downlink in the base station, with uplink in the UE, and it won't work. Okay. So that's the reason why we talk about averages. I'll illustrate this in more detail in the first slide of today. So let me see, okay to this. The other point to take away is this. Okay, this is the throughput region. Every point on this throughput region refers to a possible rate pair. I can get this rate pair, I can get this rate pair, I can get this rate pair. In M dimensions, I can get any of the M rate pairs which are enclosed in the throughput region. I cannot get this rate pair, I cannot get this rate pair, and I cannot get this rate pair. Any rate pair outside is not achievable. Okay. The other point is that what does it mean to achieve a rate pair? It means that there is a scheduler which one can find. So it's a mathematical statement. There exists a scheduler which will achieve that rate pair. Okay, for example, I told you that this rate pair, which is 0 to UE1 and 130 to UE0, can be achieved by always scheduling the best UE. If I schedule the best UE in the orange state, I get 160. In the blue state, I get 100. On the average, we get 130. So there's a scheduler which achieves this. How does this get achieved? It achieves by scheduling each of them half the time. Okay. It's achieved by always scheduling the best UE. So whenever the orange rate region prevails in an orange slot, I will schedule the best UE, which is the UE0. When there's a blue slot, I'll schedule UE1, which is 120 Mbps. And since the orange and blue are 50-50, I will get a point in the middle of this line, which is this one. So I've shown you a scheduler which achieves that. It is the best UE scheduler. This scheduler always achieves always schedules UE1. So you get you get 90 Mbps. So an important point to realize is every point in the rate region is achievable by some scheduler. Okay. And there's no scheduler for a point outside the rate region. Okay. All right. Again, I went over this quickly at the end of the last lecture, and I asserted that the rate region, which is a region, it's a set of points in m dimensions, is a convex set. Some of you may remember this from your math courses in university. But what does a convex set mean? A convex set means that if I take 2 points in the set, and if I join those 2 points by a straight line, by a line joining the point in m dimensions or whatever number of dimensions, then every point on that line is achievable, is a point in the rate region. Okay, so I just stated that formally. What does it mean in practice? What it means is this. As I told you earlier, just in the last slide, if I take this point in the rate region, there's a scheduler which achieves that. Okay, some scheduler can be designed to achieve that point. I may be interested in that. I may be interested in foregoing some throughput for some reason. We'll see that a little later. And you can achieve that by a scheduler. Scheduler, let's call it S1. And a scheduler S2 can achieve this point. How do I achieve any point in between? What does it mean to say we can achieve any point in between? What it means to say is you can do time sharing. Okay? Time sharing means half the time I use scheduler S1, half the time I use scheduler S2. So the scheduling mechanism has available to it 2 schedulers, S1 and S2. In a particular slot, it tosses a coin with a probability of half. It chooses scheduler S1 and schedules with that scheduler. In the next slot, it again tosses a coin. And then the coin will fall S1 or S2. So whenever the coin falls S1, schedule S1. When the coin falls S2, schedule S2. By doing that, I will get this point, the midway point between those 2 schedulers. Okay? How do I get a point which is close to this scheduler? I schedule this scheduler more often and that scheduler less often. So by time sharing between 2 schedulers, I can get every point. So as I said earlier, every point in the rate region is achievable. If 2 points are achievable, you can achieve any point in between by time sharing between them. That's all it is saying. So time sharing is available to us in the scheduler. Okay. All right. Let's go to the next point, which I made last time. This was a bit more subtle. Let me repeat that, but it's a very important point which will be useful in the discussion that I'll start with today. If I have a point in the rate region, let's take this point. Okay, this is a rate pair or an m-dimensional vector, and I've already asserted that there's a scheduler which can achieve it. What I'm asserting is that if you can achieve this point, you can achieve any point in the rectangle here. Because every point in the rectangle has only a lower rate. If you can achieve, say, I don't know what this is, maybe this is 80 Mbps for UE0 and 50 Mbps for UE1. If you can achieve 80 and 50, 80, 50, I can certainly achieve 60, 50. How do I do that? I do that by wasting time. Scheduler S achieves this point. Sometimes I simply waste time. I say, the scheduler will schedule, let's say, how do I get this point? I get this point by retaining whatever the scheduler is giving for UE1, but then just not giving UE0 all its time. Okay, so I can get every point in this rectangle by simply wasting time. The scheduler schedules something, I just don't give it that time. Okay, so this is the essence of coordinate convexity. The name is a bit unfortunate, but maybe there is some deeper concept there which I don't know. Now look what happens here. I have drawn here a boundary of the rate region which sort of curves inwards. It's a bubble-shaped boundary. Okay, and let's suppose that this boundary could happen in the rate region. What will it mean then? Suppose I take this point. And I know that from the physics that I just explained to you, I know that the rate region is coordinate convex. Take this point and draw a rectangle from this point towards the 2 axes. What do you see now? What you see now is that there's a little portion of the rectangle outside the rate region. That means by the principle of a rate region, I cannot schedule this point. Okay? But I know that I can schedule the point. If the rate region was practical, I can schedule the point. And if I can schedule this point, I can schedule every point to its left or below it. So what went wrong? What went wrong was this boundary has a slope here which is positive. Okay? What is the positive slope of the boundary? What does it violate? Look what's happening out here. If I increase one UE's rate, the other UE's rate also increases along the boundary. But that should not happen. The boundary is a constraint. It should look more like this, that if I increase a UE's rate, the other UE's rate decreases. Okay, that's a fair statement, right? Now, what does it mean in terms of the geometry of the boundary? Draw a tangent plane to the boundary. The tangent plane here has a negative slope. If one UE's rate increases, the other UE's rate decreases. On the other hand, the tangent to this boundary, one UE's rate increases, the other UE's rate also increases along the tangent. So it cannot happen. Okay. So what this is saying is that coordinate convexity in turn implies something very important for us, that all tangents to the boundary will have positive coefficients. They'll be of the form A1 theta 1 plus A2 theta 2 plus A3 theta 3 plus AM theta m equal to a constant C. The equation of a straight line or a plane that you learned in first year of engineering. Okay, and the A's are all positive. Okay, so for example, this line has an equation like this: W0 theta 0. Theta 0 is the throughput of this fellow. W1 theta 1 is the throughput of this fellow. W0 and W1 are weights. You'll see why weights are important in a few minutes. Equal to C. The equation of that line is of this form. W0 and W1 are positive. Now, if you transpose, let us say the theta 0 term to the right, you'll see a negative coefficient out there. And the slope is negative. Okay. So, what's the takeaway from practice? For any throughput vector in the rate region, for every rate vector with smaller coordinates, there exist schedulers that achieve such rate vectors. Hence, they are also in the rate region. The reason is you can always waste time. The tangents of the boundary will have negative slope, like shown out here. For m dimensions, the coefficients of the tangent plane cannot be negative. They should be all at worst 0, but positive. And the positivity of the coefficients, if you transpose it to the right-hand side, you will see that you will get the physical property I explained. But the boundary increasing one UE's throughput cannot lead to another throughput also increasing. By the way, having said that, this is a property of this particular physical system. There is a base station controlling several UEs. This property fails in Wi-Fi. I won't spend time on that, but this property fails in Wi-Fi. In Wi-Fi, you can increase one UE's throughput, one link's throughput. Another link somewhere, the throughput can actually increase because of some complicated processes that happen in Wi-Fi. We'll leave that alone, but just as a something to keep in your mind that this property is specific to this system. Okay. Now, this was the last slide last time. I want to dwell on it for a couple of minutes. Now, let's take this boundary. This is a throughput region where I put numbers, and it's no longer abstract. This is from a simulation, a throughput region where this UV can achieve maximum 100 Mbps, this 30 Mbps, and this rate region boundary. The boundary is now smooth. Why is the boundary smooth? Remember, when I had two possible rate pairs, 120 and something and 90 and something, I forget the numbers. Then you get two triangles. If you mix the two triangles, you can only get a polygonal rate region with some flat boundaries. In practice, you will have maybe up to 30. Remember the table I had shown, the MCS table? You have up to 30 MCS values for each UE. Okay, so you have 900 MCS pairs. When you take those 900 possible triangles and you mix them together, you get a relatively smooth rate region. And in mathematical models, we often assume something called Rayleigh fading or Nakagami fading, where in fact the MCSs are continuous for mathematical convenience. So that's why you get a more smooth rate. Now let us take a tangent to the boundary. A tangent to the boundary. And let us see whether the tangent will touch the rate region. Let's call the point x0, x1. So what do? We take a tangent. I wish my pen was working otherwise. Anyway, let us take a particular slope. They should all be negative slopes and move them up and down. Move the slope up and down. Move the line up and down. Let's move the line until, so now I want to maximize the value of this line. Okay, it is W1 theta, it is W0 theta 0 plus W1 theta 1 is the value of that line. Why value will come in a minute. Okay, let's suppose, why should I postpone that? Suppose I was to evaluate the throughput I am getting by linear combination. Okay, let me step back a bit. In practical networks, there are hundreds of UEs. You may have tens of base stations, each with tens of UEs. There are thousands of numbers. How does the operator, how does the network designer represent 1,000 numbers, 10 base stations, each with 100 UEs? 1,000 numbers. Okay, I'm trying to optimize the network and I have 1,000 numbers to optimize. Very complicated. So what operators have done, and before this, economists have done that. 1.4 billion people. How do you distill the way the economy is functioning? You can't report 1.4 billion incomes. It makes no sense. So you have a notion of utility. Economists coined that many, many years back. And telecom people adopted it maybe about 30, 40 years back, around the 90s. Notion of utility. Every person is getting a utility from the economy, from the network. Then we distill that together into a network utility. Okay. So one measure of network utility is very simple. User 0 is getting the throughput theta 0. User 1 is getting a throughput theta 1. Let's distill that by saying I'm going to give a weight to user 0. I'm going to give a weight to user 1. I'm simply going to take a linear combination. Okay. That is the utility of this particular throughput pair. So utility of this throughput pair theta 0 theta 1 is W0 theta 0 plus W1 theta 1. And all throughput pairs in this line are going to give the same utility. That's the meaning of the line. W0 theta 0 plus W1 theta 1 equal to C, constant. Okay? So all points here have the same utility. But I'm not satisfied with that. I can get more utility. So the operator does something, changes the scheduler, and moves this line up a bit. Maybe moves it to here. Get even more utility. What's the maximum possible utility? I keep moving the line until the line just begins to leave the throughput region. If the line was moved all the way up to here, it's not feasible anymore. I can't schedule that. So I move the line only up to the point where the line just touches the throughput region. It's a tangent now. Okay. And now this pair x0, x1, where the line just touches the throughput region, is the best possible throughput pair. Okay, because the C, let's call it say C prime, and the C for this C prime is more than C, and C prime cannot be made anymore. Cannot be made anymore. Okay, so if I choose my weights for throughputs at W0 and W1, best possible operating point is this, and there are mathematical results about that. It's called a supporting hyperplane. Supporting hyperplane of a convex region maximizes the corresponding, weighted sum. Okay. Now, there is another very important usefulness for this idea. Remember, I do not know the rate region boundary. No one told me the rate region boundary. Rate region boundary is not given to the operator by somebody Nokia giving the operator a drawing on a slide or a paper. Okay? The rate region boundary is implicit. Implicit in what? Is implicit in the links that are created by the radios that I'm using. I'm using the radios, I'm using a modulation scheme, there are 100 UEs down there. Now, only by experimentation can I learn the rate region boundary. How do I learn that? Well, we make measurements over time. We take a particular utility. I take W0 theta 0, W1 theta 1. I run an algorithm to maximize utility. If I run the algorithm for a particular W0, W1 pair, I will get this point. Then I change the W1, W0 pair, and I may get this point. I may get this point. I may get, experimentally, I can keep on running the network for different schedulers and for different W0, W1 pairs to get a bunch of points on the rate region. In practice, no one will do that. But in the laboratory, we do that because we want to understand how things are working. No operator will do this in practice. But as engineers or designing things, we have to understand what the rate region is. Okay, so we learned two things. How do you maximize linear utilities? The optimum is going to lie on the boundary. The tangent plane touches the boundary. And how do you draw the rate region? By experimentally running different schedulers for different Ws and then getting the rate. Now, what scheduler will give you W0, W1? That we will learn in a few minutes. Okay. How do you schedule the network to get to this point? or to get to this point, or to get to this point. What scheduler will give you that point? Okay. All right. So thus we can discover the boundary by optimizing this utility, W0 theta 0 plus W1 theta 1, for all theta 0, theta 1 pairs in the rate region. And if you go on varying W0 and W1, you will get all the points on the boundary. Now, the particular pair W0 equal to 1 and W1 equal to 1 is what? It is the maximum sum throughput pair. Suppose the operator is only interested in maximizing the sum throughput. Suppose the operator makes revenue based upon bits per second transferred. Okay, suppose its revenue model is, I will get so many rupees per kilobits of data transferred per second, and I only want to maximize revenue. If that is the operator's utility, this is where you will operate. Okay, why do we operate here? Well, now you look at lines with slope of 45 degrees because W0 and W1 are equal. The angle is 45 degrees. So you'll get a line something like this, maybe. Okay, I wish I could draw, but that's the line you will get. Now you keep moving that line from here to here, from here to here, and ultimately you'll find the line touches this place. Okay, so this is the point, the operating point, which maximizes sum throughput. The operator's total revenue is maximized if revenue is proportional to throughput that it gives to the users. But look what the problem with that is. The problem with that is that because of the fact that UE1 is further away from the base station, U0 is close to the base station, you get a very unfair throughput. Okay? UE0 gets almost the maximum throughput, whereas UE1 gets only about 5 Mbps, which is a small fraction of its own maximum throughput. This is the so-called proportional fair point. This is what is operators often use this point. It is a practical point that operators often use. Okay, and we will spend a lot of time understanding the proportional fair point, its properties, how you schedule for it, why it's called proportional fair, and all these things. And you can see that this proportional fair point will not achieve maximum throughput because the maximum throughput point is unique. Now, there's some theory which tells us that you can't, there can't be 2 points which achieve the maximum throughput, at least for this kind of a curve. Okay, and this point will not achieve maximum throughput, maximum sum throughput. So the operator will have to forego some throughput, okay, and have a different revenue model to also give fairness to the users so that the users don't leave its network and go to some other network. Okay, before we go any further, I want to discuss one very important algorithmic, yeah. It did not always do what? No point outside is achievable. Any point inside can be improved. So that's what I was saying here. You can find a point, you just draw a line at 45 degrees angle, okay? Then all the points where the line intersects with the rate region are points which will achieve the same throughput, okay? But now let's move the line further and further outwards, thereby getting more and more sum throughput. Ultimately, the point that will achieve the maximum possible sum throughput will be on the boundary. No, I'm saying that let's make the weight equal to 1. Okay, then you get a line W0 theta 0 plus W1 theta 1. It's a line now equal to C is the line. W0 is 1, W1 is 1. So theta 0 plus theta 1 equal to C is a line. If I take that line here, I take a particular value of C, let's say 100 Mbps. Then all the points along that line of line 45 degrees are going to get 100 Mbps. Okay, maybe not 100, but maybe 95 to 100 Mbps. Okay, now, but I can do more. Let's take 80 Mbps. Okay, I can do better. How do I do better? Move the line outwards. Now you get 85 Mbps. I'm not happy with that. Ultimately, I can get 100 Mbps, which is here. Just keep on moving parallel lines outwards. Now, one very important algorithmic step that we use in algorithms, in network algorithm in particular, is averaging, simple averaging. You all know what averaging is. In this room, there are 50 people, and each one's height is whatever, 172 centimeters is my height, 170 centimeters, whatever. You take an average of that. Okay. So averaging is a very common thing that we do in statistics. Now here we have to do averaging over time. You don't want average throughput, for example. You want the average probability of something happening. You make measurements. There's a particular way to make measurements, averaging that we do in networks. In TCP tries to measure the average round trip time. It keeps on looking at acknowledgements that it's getting back from the endpoint. And it looks at the round trip time. It sets the timer when it sends the packet out, it gets the acknowledgement back, it gets a round trip time. It takes the average of that. Okay. How do you take averages in networks? This simple one-line algorithm is good to understand. Some important properties that it has. The algorithm is called EWMA, exponentially weighted moving average. Many of you would have seen that. It's good to understand what's happening. Okay. Now let's begin to look at what algorithms do, what schedulers do. Let's suppose that a scheduler, some scheduler, now here I'll have to begin to use some notation. Please bear with me. All being engineers, I'm sure some notation will be acceptable. Okay. So here K indicates the slot index. K is 100, 101, 102, 103 slot index. I is the user index. So let's say BKI is the number of bits I gave to user I in slot K. Okay. So I may have given user I, what I'm doing is I'm filling up that OFDMA grid. And in the OFDMA grid, I may have given, let us say, 10,000 bits to user 1 now. Then in the next slot, I gave 20,000 bits to user 0. And in the third slot, I gave 15,000 bits back to user 1, so on and so forth. So BKI is just saying that in the 100th slot, I gave user 0 so many bits, and every slot I'm giving some bits. Okay. For example, BK0 could be 0 kilobytes, 0 kilobits, 50 kilobits, 80 kilobits. Okay. For example, if you did not serve the user in a particular slot, you've given it 0. If this was the rate pair, then I would have given it 50 kilobits. Okay, because this is 0.5 milliseconds, remember. TTI is 0.5 milliseconds. So although it says 100 here, 50 kilobits in 0.5 milliseconds. I would have given 80 kilobits here. So 0, 58. I'll use a notation T for the TTI duration. TTI is the slot duration, which is 0.5 milliseconds in one of the numerologies. Now, theta ik is the average throughput of UE until the TTIK. What do we do? Let's suppose we're looking at the 1 millionth slot. I take the rate I gave it in the first slot, in the second slot, in the third slot, and average over 1 million slots. Let's call that theta ik. Throughput averaged from the very beginning over all the slots. Okay? Theta I bar k, which I'll define now, is the exponentially weighted moving average. And I'll discuss what it means and what the advantages are in the next couple of slides, because we'll then begin to use it. So theta ik is the natural average. Theta I bar k is a moving average with an exponential weight. Okay. This looks more complicated than it really is. I'm just showing you averages. Theta ik is what? Theta ik, I'm at the kth slot. So j equal to 1 to k, 1 to million slots. How much did I say? In the jth slot, I gave user I BJI bits. BJI bits in the jth slot. Divide by t, that is the duration. So this is the throughput I have given to user I in the jth slot. So this is the average throughput. I gave it 80 Mbps in this slot, or 160 Mbps in this slot, 90 Mbps in this slot. Average that. That's all it is. Now let's leave this very simple calculation aside. It's just algebra. It turns out you can write this average in the following recursive fashion. What does it do? It says you take suppose I want to update the average in the kth slot. What does it say? Take the previous average until the k minus first slot. Take the throughput I have given that user now, subtract the previous throughput, okay, and divide by k, 1 by k. Simple, okay? So it's like we are adjusting the average. I got an average till the k minus first slot, and I adjust the average in a particular manner. I take the current throughput, subtract the previous throughput. If that is more, then I will slightly improve the throughput. If that
Sir,
is less,
sir, this formula is as per 3GPP or as per the observation and calculation we are doing here?
3GPP you'll see now. I'm introducing to you just normal averaging. Okay, 3GPP is EWMA. I'll just come to that.
Okay, sir.
This is normal averaging. If I was just normally average, okay, and I'm motivating the 3GPP averaging. Okay, so the normal averaging can also be written in the recursive fashion. Previous average, the average given in this slot minus the previous average multiplied by a coefficient, by a step size it is called. Okay, let's modify that in this way. This is what is the 3GPP as he's calling it, but this is a very old, it predates 3GPP by decades. So theta I bar k is the EWMA average. What do you do in EWMA averaging? You take the current throughput, okay? This is the same as here, current throughput. Let's pull the 1 over k inside, put the 1 over k inside. So I'm multiplying the current throughput by a number, by a weight in some sense. I'm going to use a different weight out here, okay? What is this weight? This is a geometric weight. Okay? I choose the number alpha between 0 and 1, 0.01, 0.9, 0.1. Each of them has a different implication we will see in the next slide. Let's suppose I take the number 0.1. The 3GPP recommendation is 0.0005. Okay, we'll see why. Let's take the number 0.01 with alpha. Then, now let's take this j equal to 1 to k. 1 to 1 million, I'm at the 1 million slot. I multiply the current throughput I've given to the UE by alpha, by 0.01. And then I multiply the previous throughputs I have given by decreasing numbers. Okay? So look at this. When j is equal to k, the current slot, I multiply only by alpha. When j is equal to k minus 1, I multiply by 0.99, because 1 minus alpha is 0.99. When j is equal to k minus 2, by 0.99 squared, 0.99 cubed. So going backward, you can see a curve like this. I am giving less and less weight to past history. Whereas with 1 over k, I'm giving the full weight to the entire history. Okay? So this is exponentially weighted. This is exponential weight. The past history is given less and less weight. All right. Now you can look at this algebra at home. This algebra is very simple. This algebra is similarly simple. All we do is we take out the last term. The kth term is taken out here and rewrite the rest of it by taking out 1 minus alpha. And you find that you are left with the previous average. Okay? So that's what it is. 1 minus alpha times the previous average plus alpha times the current given throughput. Rewrite it and you'll find it in the same form as this. Same formula, the same form. The previous EWM average plus a constant now, not 1 over k, it's a constant, alpha, 0.01, times the difference between the rate given now and the previous average. Okay? Why is it called exponentially weighted? Because of this weighting. Okay, in a particular slot, I'm weighting the previous history in an exponentially decreasing manner. Okay. So this is a very similar structure to this with a constant weight. This is the implication of that. Okay. Let's see what happens. Let's take a particular realization of the throughputs that two UEs, not the throughputs, the channel rates that two UEs are getting. From 0 to 1, 10,000 slots. Channel rates that in each slot, the two UEs got, the blue and the red. Well, these I've shown this diagram, this picture to you before. So let's suppose that at 4,000 slots, this UV got about 80 Mbps and this UV got 30 Mbps. Okay. Let us see what happens. Suppose we give the entire channel to UE, the blue UE. You only schedule the blue UEs. Let us see what average rate it gets using the two averages, the EWMA average and the normal average. I plotted that here. So what I did was we are giving the entire rate, every slot to the blue UE. If you use the normal average, this is what you will get. You will get, well, however the channel was varying, you get a slightly larger throughput than 100 Mbps, and over time it becomes 100 Mbps. Where did 100 Mbps come from? Recall the rate region. Let me go back to the rate region. Okay. I'm looking only at the blue state. Sorry, forget that. Yeah, this is a different example. I'm sorry. So if you were to average this, remember this is over 0.5 milliseconds. So 80 here means 160 Mbps, 90 means 180 Mbps, 70 means 140 Mbps. If you average this, the lows and the highs, over all time, you get 100 Mbps. That's what this is showing. 100 Mbps is the average throughput the UE will get if you only schedule that UE, the blue UE. Let's take an EWMA average of the blue line, the blue plot, with alpha equal to 0.00000. It turns out, and I'll show this in the next slide, that 0.001 means you're averaging over the last 1,000 slots. You're forgetting the history, last 1,000 slots. Now you see what happens. This average builds up slowly, fine. But you see it's capturing local behavior. For example, here, the channel was poor for UE, for that blue UE, and it captured that. This one did not capture that because it already has too much history built up. It was taking the entire baggage of tens of thousands of slots to maintain the average. Okay, there was an increase in the channel was good here. You got a slight increase in the throughput. Channel was poor here, so you see that variations, local variations. Okay, why is that important? It's important because channels in practice are not stationary. You do want to care about local behavior. UEs are not static, they keep on moving. If a UE moves away to a poorer location, you keep having the baggage of 1 million slots, you won't realize that the UE has moved to a poorer location. So it's important to maintain local history rather than the entire history. Okay, we will talk in the next slide that in fact EWMA is not keeping the entire history. It's in a very sort of simple manner. Just imagine how you will do it if you do not know EWMA. What will you do? You'll keep a register in your code, a register of 1,000 slots. And the register has to be constantly refreshed. You have to shift left and add one more piece of data. Shift left, add one more piece of data. Very heavy in practice. Imagine keeping for 100 UVs, hundreds of registers in your base station. Sometime we'll discuss this. The half millisecond that you have in 5G requires a lot of work to be done. All the physical layer work or scheduling work. You want to minimize your compute in the half millisecond. So this is a simple way of averaging over 1,000 slots while not having to keep a register of 1,000 slots. Okay. So now let's review the EWMA averaging. Theta bar I is this. I've already shown that. Let me remind you, this is the throughput I gave the user I in the jth slot. I could be 100. And this is the weight I'm giving to the user to the previous history. So when I'm averaging, I'm weighting the previous history by exponentially decreasing average. Now let's do a small calculation. Again, don't bother too much about the math there. Go home and look at it. Let's suppose I asked the question, what is the weight I gave to a history 10 steps back? Okay, you see here, the history, the current history was given the weight alpha. The history 2 steps back was given the weight 1 minus alpha times alpha. The history 10 steps back was given 1 minus alpha to the power of 9 alpha. Okay, the history is getting less and less weight as you go back. What is the average history I'm keeping? Okay, can I average this? Okay. First of all, you'll notice that if I sum these weights, if I sum the weights over all history, simple calculation, your geometric series, it adds up to 1. The total history the total weights is adding up to 1. Well, if it's like probability then, probabilities add up to 1. Let us take the average weight. What do I do then? I multiply each weight by the history. So this is the amount of weight given to the history of length L. Multiply that. Add it up. Okay. Adding up this series is something you might have learned in first year math, calculus. It requires a little bit of a trick. You can do that. You get 1 over alpha. Okay. The way you do that is you take the geometric series and you simply differentiate that and then you can obtain it from there. Anyway, let's suppose you can sum this in 1 over alpha. What does it say? With the average history I'm keeping, the average amount of looking back is 1 over alpha. This is simply a rough representation. Actually, you're looking back all the way to your first sample, but you're giving less and less weight. But from an engineer's point of view, it's like you're keeping about 1 over alpha of history. Okay, 0.001, 1,000 slots of history. 0.0005, the recommended value in 5G, is 2,000 slots of history. Okay, so that's 1 over alpha. This calculation I have shown a different way for those who are interested, but I'll leave it alone. Okay. So this is the reason why we say the averaging window of EWMA. Can I get some water, please? The EWMA is 1 over alpha. Okay. All right. Now, this is a bit of math, which I don't want all of you to really sink your teeth in, but it's very important math for those who are interested in some of these things. What is the connection between EWMA and the normal averaging? Mathematically, they are very similar, even though they look very different. It turns out that if you let alpha go to 0, if you let your alpha go to 0, then history goes to 1 over alpha, history goes to infinity. It turns out when alpha goes to 0, the EWMA average becomes large. This is something so you can go check it out from the appropriate book, but just to keep it on record for your reference, I won't dwell on that. Okay. All right. Now, having learned something about rate regions, having learned some properties of the rate regions, having learned about rate region tangents and so on and so forth, I've learned the properties of the boundary of the rate region. Yeah.
Instead they continue to pay actually reduce the
Yeah, you can. You can try different weights. The exponential weight is the easiest because you're able to, okay, there is a very important property of the exponential we can discuss offline. It is called the memoryless property. And for that property, exponential is unique. Geometric in discrete time and exponential in continuous time. It's a unique solution. So you cannot get a memoryless thing, which other than exponential. Also, it's very convenient. You multiply by a number. Other way, for whatever reason you want to use them, may require more complicated calculations. So we leave that out.
Ease of calculation.
Yeah. The ease of calculation, the best way of keeping history of 100 is to keep a register. You keep all the data and you keep shifting out. Not practical. Okay. Now, you have this huge rate region to operate in. Okay. In m dimensions, it's a complicated entity. Now, where do you operate in the rate region? Where should the operator operate? Okay. Not only the operator, because now there's a lot of talk about private 5G, whether it business-wise, whether it is going to happen or not, but it has to happen because industry will soon require wireless. Even now it requires wireless. So where would you operate in the rate region? The rate region is giving you a constraint. Where do you operate in that? Okay. So to do that, I want you to now remember the first slide I gave last time. I talked about a variety of different traffic. Okay. I talked about this browsing traffic, downloading traffic. I talked about the more currently important real-time robot control. I talked about AR, XR, VR, real-time streaming video, a cricket match being streamed to the people. Okay. Streaming video can be important also in industry because you want to observe a process on the shop floor in real time. You don't want to have operators sitting out there. It may be dangerous. You want to operate it. A nuclear reactor, you want to have real-time streaming. And you can't have wires from there. You have to have wireless. So you want to be able to observe things in real time, in milliseconds delay. Okay. Now, I want to build a concept in your mind of open loop and closed loop flows. If you remember the picture I had drawn of TCP, how does TCP work? TCP works like a conveyor belt. There's somebody at the server loading the conveyor belt and somebody at the receiver unloading the conveyor belt. Okay? If the person at the receiving end slows down, the conveyor belt will indicate back to the loader that the conveyor belt is getting full, so let me not load anymore. TCP is exactly that. When the window closes, TCP stops. So there is a feedback, a constant feedback. Okay? And what is TCP's objective? The TCP's objective is to keep the bottleneck full. If the bottleneck starves, the wireless link is being wasted. Okay. In fact, recently I heard from a developer that they were getting very poor throughput, and they finally had to tune their TCP, the physical link behavior, because what was happening was the TCP window was shrinking, and the actual queues at the base station was starving. Okay. So the objective of running TCP over wireless or anything is to keep the bottleneck link full. At least it should not starve. So the moment it starves, you're giving no throughput. Okay. You can have it full with a lot of data, doesn't matter. It should not starve. So if the queue is always non-empty, the scheduler is able to optimize its behavior and able to give the right throughputs to everybody. Okay. Remember that a boundary is achievable only if the buffers are full. Otherwise, if UE0 buffer gets empty, I can only schedule UE1 and it may be in a bad state. What do I do in that case? I'm just wasting. So not letting the queue starve is desirable. Okay. And it's called closed loop because there's constantly this conveyor belt kind of behavior happening there. Okay. On the other hand, if you look at streaming video, an edge controller controlling a robot, it's closed loop, it's real time. Okay. Now, some people will say, well, video is not really open loop. There's RTSP running on top. RTSP, which is an application level protocol, keeps telling the sender, look, the video is not doing too well, reduce the coding, and so on and so forth. But that is not really something which is going to be useful for real time. In real time, the video, first of all, should not degrade. It's doing something very important. The robot control should not degrade. The robot will probably have a failure. So you cannot depend upon these higher level feedback loops to keep things in order. Okay, so maybe there's some gray area in between, but let's talk about the extreme. You cannot have a feedback loop controlling the source of data. The video rate drops, the frame rate drops, the voice quality drops, not a lot. Having said that, there are very interesting problems in robotics over wireless about actually optimizing the way you make measurements, optimizing the way you send control messages over wireless to be able to exploit the fluctuating quality of wireless. Those are interesting problems of relevance in a different topic altogether. So let's assume we really want to do well for this data which is moving one way, and there is no opportunity for controlling the source. Okay. Now, so real-time interactive streaming like video conferencing, AR, VR, they typically go over UDP. There is no control at the protocol level. Now, let me show you one diagram, one plot. This is a very fundamental plot. Anybody who's taken a course on networks or performance of systems would have seen this plot. There's a very famous model called the MM1Q. It's a queue. So what happens is, think of this as the queue. There are entities coming in, and there's a server. The entities has to be served by the server. Now, if you think about it naively, suppose you're a hardware designer. Okay? The hardware designer, you are processing packets coming in a router. What you could say is, it'll cost me maybe $10 more to design this piece of hardware. If I was to give only a 90% occupancy, I'll design it so that my stated rate of 10 Gbps is exactly matched by the hardware I'm designing. 10 Gbps coming in, 10 Gbps is my hardware design at which the hardware can process. It's a disaster because packets coming in will never come in smoothly. They will come in bursts because of whatever is happening in the past. So one should never design open loop processes for exact match of the server speed to the input rate. What happens if you do that? This is the input rate at which packets are coming into something, to a router or whatever, or a base station. And look at the mean delay. Look at the delay that the packets suffer. Let's suppose that the server's rate is 1, just normalized. Server's rate is 1. As the input rate, so you could say, I'm going to match the server's rate. I designed my hardware to match 10 Gbps, which is the input rate. Okay, my link is 10 Gbps. I'm going to design the hardware for 10 Gbps. Look what happens to delay. Delay shoots up. Okay, so if you're concerned about end-to-end delay, you're concerned about real-time video, real-time robotics, and so on and so forth, one should always pull back. There should be a pullback from 100% occupancy. Okay, which means that you should not operate on the boundary for real-time traffic. Okay, you should only operate maybe somewhere here. Open loop real-time traffic must not be scheduled in the boundary. So the boundary is like you're exactly matching the service rate with the input, and queues will build up. Okay, so if I could have drawn a three-dimensional picture, I would have shown you the queues are small here. Let's suppose there are 2 videos being served on this thing. I cannot have, okay, this thing is covering it. Let's suppose this is 30 Mbps and the other side is 10 Mbps, 100 Mbps. If I had 100 Mbps, 110 Mbps video and a 40 Mbps video, I can't handle that. That puts me here. So clearly the 2 video rates will have to be inside somewhere if I'm handling it. But they can't be on the boundary now, because on the boundary, the video delays will shoot up to infinity. They have to be somewhere here, somewhere inside. Okay, it's a design issue where I am. And then the interesting question is, what if you are handling some bulk traffic and some video traffic? All right. So I've given you a feel for, we have now brought these sort of descriptive views of different kinds of traffic down to understanding when the rate measurement should be operated. Okay. Now I'm going to come back to real time only much later, maybe in my third lecture, probably near the end. And I'm going to spend most of the time now in talking about these non-real time flows. Most operators, I think they care too much about real time. They are more interested in serving internet users and these operators the point of view of the transport traffic. The boundary is around huge bunch of points.
Yes.
Yeah. Yes.
Just take a minute then.
Do we need to do the second page as well?
So what we're going to do is we're going to define some functions. The utility of the user theta 0 is a function u0. It could be simply a constant. It could be simply w1 w0 times theta 0. So it could be a simple function. u1 times theta 1 is a function of the throughput. Okay, and u1 times theta 1 could be simply w1 times theta 1. So it could be a simple linear function. In general, they are non-linear. Okay, we'll see some examples of that. So what is ui theta? Ui theta is the way user I evaluates its utility. Okay, utility is a very is borrowed from economics. You must have, those who have taken a course in economics. I remember taking undergraduate economics courses. First thing you learn about is utility. Okay, if I have 100 rupees, maybe 10 rupees matters a lot to me. If I have 1,000,000 rupees, 10 rupees won't matter that much to me. The utility is typically a function which is increasing. It matters a little bit to me, but it matters less and less as I have more and more money. Okay, it is called the law of diminishing returns. So typically, this function u would obey the law of diminishing returns. It will be increasing with more and more throughput. If I already have 100 Mbps, I don't really care about 10 Mbps more. But if I have 10 Mbps, 20 Mbps is really useful for me. Okay, so this is modeling. This will model that. You'll see. All right. So then, once I have a utility function, how do I identify the point for the utility function? Very simple. You do an optimization problem. So those who are familiar with optimization, this is like a constraint region. I want my pair of throughputs to be somewhere here. Okay, the pair of throughputs I can give to my two users are somewhere here, anywhere here. I evaluate user 0's utility by this. I evaluate user 1 utility by this. Somehow I know the utilities as an operator. Where should I operate? I should operate at the point here, which maximizes the sum of utility. Okay. Suppose, let me come to that later. Suppose my, I think I'm saying it in the next slide. So let me go there. Okay. Suppose the utility of user I was throughput. I just want maximum throughput. I don't really care about any diminishing returns. At 100 Mbps, also 10 Mbps matters equally to me. I only want throughput. Then what does the operator do? Operator says, maximize the sum throughput. I showed you that. This is the maximum sum throughput operating. And we achieve that by taking the straight line with 45-degree slope and moving them until we touch the boundary. Suppose we want to, let us choose a law of diminishing returns kind of a function. Log, you know, it's steep before 1 is negative, and then it goes up. Utility can be negative. If you're unhappy with negative, take log 1 plus theta. Then utility is always positive. Okay, for positive throughput. So log will go up and then will slow down. This is the utility for proportional fair scheduling. Proportional fair scheduling, which everybody already knows about in this area, that's the utility for. So it turns out that that operating point is here. We will study this in great detail as we go along. So that's a very common. Clearly, the total throughput is smaller there because you remember those straight lines. The straight line here, the 45-degree line here can be improved until you come to this point. So the throughput is smaller and the operator will send less bits per second, but it's fairer. Okay. This is another operating point. Suppose the operator wants to give to a user, okay, I'll be proportional fair, but this user is willing to pay me more. This user says, never make my throughput less than 25 Mbps. No matter what happens, I want this throughput. I'll pay you more for that. My application requires that. We'll see applications of that a little later. I'll show you how you can build a fixed wireless access application from this thing. Okay, for network slicing. So suppose that, then this is the operating point. It turns out, now what we are doing, we are saying that I want to maximize log utility, log throughput, but I also want to give a constraint that give me throughput more than this. And there are utility functions. You can get any point in between you want. Just have to come up with a function which will achieve that. Okay. So the operating point is obtained by solving the automation problem. What problem? Maximize the sum utility such that the, I should probably remove this from here.
Sir, when we are giving throughput range to particular UE, this is also called, now new terms we are discussing, soft quality of service.
Soft quality of service.
Yeah.
The term soft normally comes in a little later. Hard quality of, so this is all soft. It is just throughputs.
Yes,
Okay.
yes.
Throughput is really a soft quality of service because throughput is a long-term measure. It says that over 2000 slots give the person 20 Mbps. It doesn't say that in every slot give 20 Mbps. Okay. That would be a hard quality of service. Pure throughput is over 2000 slots give 20 Mbps. Hard comes in somewhere else also when we come to hard deadlines. Ensure that this packet is delivered in 20 milliseconds. It's a hard deadline. A soft
If
deadline
not,
would be, sorry?
sorry, sir. If not delivered, directly we need to drop the UE in hard quality of service.
I didn't follow the question.
Sir,
Directly?
in case of hard quality of service, if we are not getting hard quality of service, then we need to drop the UE.
Okay. We'll come to all these things. Admission control. You
Okay,
might not want to drop UEs because I don't know, at least many years back, telecom operators dropping was considered to be a
yes,
bad
yes.
thing.
Mhm.
So you don't want to drop into admission control. If you cannot admit the call, whatever the call might be, then and then there's handover. So when you do a handover,
yes,
suppose
fine.
you have a hard deadline call, flow, and you hand over, then you'll have a more strict requirement for the handover.
Yes,
Don't
sir.
hand over unless you can accept the call. Don't hand over. You may have a drop at that time, but then you'll have a drop with a very low probability. Okay. So the optimization problem becomes maximum sum utility over all thetas in this region. Okay. So optimization, it turns out, is a very important conceptual basis for scheduling. And anybody who wants to do research in the area should take a course on optimization. All right. Bring this back here. Okay, now we begin to do scheduling. What is a scheduler? A scheduler is basically a mapping from data to action. Okay. What is the data the scheduler is working with now? In a particular slot, so TTI is the 5G term for a slot. What does TTI stand for? Transmission time interval.
Yeah.
Okay. Transmission time interval, TTI. I'll call it a slot. This is slot K plus 1. This is the scheduler which we have chosen. The scheduler has to do something. The scheduler decision is going to be schedule UE0 or schedule UE1. Why am I saying that? Schedule UE0 or schedule UE1? Why can't I schedule both? Remember, I have assumed in the very beginning that this is TCP transfers. Lots and lots of data is there. So I have enough data. I can schedule what? 20 packets from one user in one in one OFDMA grid. I have 2 megabytes of data of each UE sitting out there. I'll serve 20 packets from this fellow and 40 packets from this fellow, depending on the MTS that person uses. Okay. I'll fill up my transport, I'll fill up my OFDMA grid by UE0 or by UE. This is what I'm assuming now, because we have full buffer traffic. So the decision is UE0 or UE1. We come to combination of full buffer and real time, for example, later. So the decision of the scheduler is only this or that. The scheduler has this data. Suppose there are n UEs, the data is correspondingly multiplied by m. we know it's the throughput that we have given to each of the bar of this EWMA throughput. The EWMA throughput that it gave you is 0 bar cadence. 1 bar cadence. And the MCS that 0 has such fast. MCS that you 0 has engaged lot of this. MCS that you has this. The M-dimensional, the MUVs, you have M throughputs so far. MCS is ask somebody who's all this is the past, all this is if you have a control theory mindset, you may ask, okay, what about all the data in the past? Okay, it turns out you require only this data. And if somebody wants to know how that is proved, come and see me. I'll tell you how to look for the answer for that. Okay. So what do? We first of all convert the MCS to bits. How is that done? You look up the MCS in the table. In the table, you'll find that this is so many bits per symbol. You have the OFDMA grid. Multiply, as I already showed you earlier, you get 20 packets that you can transfer. Okay. Now, this is the maximum sum throughput scheduler. Okay. The maximum sum throughput scheduler is very simple. It says this. There are two users. You found that the MCSs give BK0 and BK1. Okay. If BK0 is more than BK1, schedule UE0. If BK0 is less than BK1, schedule UE. Equality you can break by scheduling the lower index user. That's it. Okay. That would have probably greater than equal to it. Simple scheduler. Let's look at the two UE's bit rates that you can get in that slot and schedule the higher bit rate. Why does this achieve a maximum sum throughput? Good question. I cannot prove that to you. Just take it for granted. Scheduling the best, you can almost see intuitively, scheduling the best user should give you the best possible sum throughput. Okay. All right. Then what do you do? So the scheduler must do two things in this slot, two activities. First of all, it schedules, okay, and then it updates the throughput. How does it update the throughput? It takes the previous throughput, it has an alpha, it takes the current throughput given, minus the previous throughput, and gets the new throughput. The other UE, it gave no throughput, and then so on and so forth. Okay, so it updates the EWMA rate. Okay, so 1130 we break here. A commonly used value for alpha is 0.0005, which now you know is 2000 slots of averaging. Okay, simple scheduler. Here's the MATLAB code for that. Simple MATLAB code. Somewhere here in the MATLAB code, you generate the MCSs. A is 0.0005. This is initializing the average throughputs. W1 is equal to 1 for both the UEs. Okay. In my code, you will find that W0 is always equal to 1 because you can always pull the W0 out. It's a common number. And W1 is something else. Okay. So W0 is always equal to 1. W1 here is equal to 1 because they're equal weights. And then you just compare the rate of, this is a 200-meter UE, this 400-meter UE, compare the rates. And that's what I exactly did in the previous slide. Get the averages in the other case, else, and keep on doing this. Accumulate the throughputs in an array and plot the throughputs. I'll show the plots in a few minutes. Okay, very simple. Okay. Let's suppose I want to go a little bit further. I want the maximum weighted throughput. I do not want weights to be equal. I want W0 theta 1 plus W1 theta 1. Very simple. Now you simply compare the weighted rates. W0 BK0 more than W1 BK1. Okay, again, why it works, again, it's sort of intuitive, but there's some theory behind this. And then you just do the averaging. Okay, so in every slot, given this, here it does not even use this. It does not use the previous throughputs, by the way. It uses only the current MCSs. Then the current MCSs convert to rates, multiply by the weights, compare the weighted throughputs in the slot, schedule the best user. This is the max weighted throughput scheduler. It will achieve that point on the boundary which corresponds to the tangent whose equation is W0 theta 0 plus W1 theta 1 equal to C. C is the maximum possible you can between this. There's an interesting point to understand here. Remember, we are doing an optimization problem. What was the optimization problem? Given the rate region is some set in the positive quadrant or the positive quadrant. There's a straight line objective function, maximize it. No one gave us that set. The set is not given to you. All you have is data that's coming at you. Yet you want to get that point on the set. You're not given the rate region. This is what is called online learning. Without being given the constraint region, you're solving the optimization problem by online learning, by getting data which statistically corresponds to the rate region. Okay? The data has noise in it. Okay? The data is not noise-free. The data has noise in it. But somehow the algorithm filters out the noise and yet gives you the right go over. And you'll see plots that I will show you. I won't spend time on it. You can figure out what it is. So in this case, you will multiply UE 400's rate by W1. And the other weight is 1, so we will just not multiply, compare and average. Okay. Now, how do you plot the throughput region? Suppose you are interested, you're curious to plot the throughput region for your little experiment in the lab. How do you plot the throughput region? The way you plot the throughput region is, now you have a loop here. For W1 going from 0.01 to 100 in steps of 0.1. So now my W0 is 1. W1 is going from 0.01 to 100. Okay, so I'm varying the slope of the tangent. Okay, and for different tangents, I'm getting different points. I do that, I accumulate the theta in an array, and I plot this. So all the throughput, all the regions you've seen me plotting have been done with this program. Okay, all right. Let's come to the proportional fair. Perhaps the most important algorithm for operators. You should understand this very carefully. There are many ramifications of this. So this picture is the same input, same action space, two possible actions. Again, convert the MCS to bits. But now what we do is we take the bits that each user gets and divide by the throughput it has got so far. Okay. And then schedule the user with the larger. These are called indices. This is called a scheduling index. So one possible scheduling approach is you calculate an index. Okay. Almost all schedulers that are used in practice have this mechanism. The data, from data you create an index. The index you massage it in a particular way. Usually you compare, and then you schedule. So indices are compared. The index for user 0 is 1, is this number. Index for user 1 is this number. You compare them, the larger index you serve. What is happening here? Let us see. There are many ways to look at this. Very interesting theories built around this. Some of that you will see as we go along. At the first sight, it's a very simple, intuitive idea. And that's probably how it was thought of in 1999 in Qualcomm. So if a particular user is already getting a lot of throughput, why give it more? Okay, so I put it in a denominator. The index is trying to, in some sense, penalize somebody for getting a lot of throughput. If somebody has a very poor channel, penalize that. Put it in the numerator. Pull its index down. So when you schedule somebody when they have a large current channel and a low throughput already given. So then the number is high. Okay? So this tends to favor users with who have not been scheduled for a while and have good channels. Okay? That's a very, very elementary way of thinking about it. We'll come to more of it as we go. Once that is done, we've identified the user to schedule. Again, do the averaging. We get ready for the next slot. So in the next slot, in this slot, we require theta bar k. So we have it ready now. And remember something I showed, maybe I haven't shown it yet, but working alongside at the MAC layer, there is a MCS adaptation going on. Okay? MCS is not constant. MCS is adapting to the channel. And so you may spend some time on that as you go along there, that it's adapting. So the MCS that was maybe different MCS here. So we have MCS pair, throughput pair. Or there could be M MCSs and N throughput. The algorithm is very simple, and the implementation is very simple. You keep track of the previous throughput. I complaint by the throughput with the previous throughput. There's no way now. It actually is one of our throughput. Rates by the throughput achieved so far. Compare and schedule. Okay. So let's see what happens. Suppose we have this sequence of frames. We get that this is good. First of all, in the sequence of rates, I got the range. That was the algorithm the very angle of the thing, you want the range. I plotted that, then I run a scheduler. I also find out the true point. There's a way of doing it. I'll tell you to do that. You can ask me offline. The true point of it is the maximum sum throughput point. Showed it earlier. You can get a true point on the boundary, which is the proportional fair point. I run the algorithm also, which I showed you. And the algorithm for maximum sum throughput gives you a blue X near to the true point and gives a blue star next to the true point. Why is the blue star not exactly at the red point, at the red star? It's because you've done this over a finite amount of time. It will converge to that point. Another reason for that is very important. The alpha is giving you an averaging over 2000 slots. The smaller and smaller you make alpha, the closer and closer you will get to this point. We'll see that practically. What is the impact of alpha on the accuracy of the control, accuracy of achieving that? We'll see that in the next slide, I think. The actual operating point will vary with time because the data that you're getting every 2000 slots is varying. Okay. Okay. And because the memory is finite, an infinite memory algorithm will converge. And in fact, these X's and star on the line is obtained by an infinite memory algorithm, just for illustration purposes. Now let's understand some algorithm that many people tend to start using without realizing how bad the algorithm is. Round robin scheduling. Okay. What is round robin scheduling? What you do is that over say n slots, you alternate. So you just take the slot index, divide by 2, and see if it is even or not. Okay. So if it is even, I'll schedule. I don't know what I say here. Yeah, in odd slots I schedule UE1, even slots I schedule UE0. Just deterministically I schedule UE0, UE. look where we reach. We get this point. Okay? We get this point. Very bad. You have to be on the Pareto boundary. You can't be here. Round robin will give us this. Now we'll see why. Maybe we'll take the break now because the next algorithm, the next explanation is very simple, but it's a bit, it requires a bit more focus. So let's go and have tea and refresh ourselves and come back and start. Yeah? Okay, we have a few minutes, maybe 4 minutes to start. Any questions?
Sir,
Yeah.
no specific question, but one thing is going in mind now. Everywhere we are talking about AI/ML integration with all the protocol stack. So when we talk about the scheduler, we have new terms are coming, deep scheduler, and how we can integrate. So do we have something in future coming days, something related to AI/ML integration with the schedulers? Some courses?
Yeah, actually, I was just talking to one of the delegates here regarding a scheduler that's been designed by NVIDIA. Maybe you're talking about that. There will be a few slides in the next lecture on scheduling on AI/ML. Actually, it's just basic deep neural networks for scheduling. I can look it up and I can probably bring some material next time. I'm less familiar with that. I must say one thing, that when somebody tells me use AI/ML, I have enough experience to be able to design something directly rather than use the machine learning. But I know going forward, the amount of work that the algorithm needs to do, in a few microseconds. So recently we had this experience of implementing a scheduler in software, Solve software. And we could make the scheduler run in 0.1 milliseconds, as opposed to running in about 5 milliseconds implemented in the traditional way. So certainly there is a lot of value to bringing in AI/ML. And we'll explore that perhaps next time to the extent that I understand it. And if anybody can give me material to study, I can also study and talk about it next time. I just heard something from Anshuman, which I will look it up. These are all very simple schedulers. They just require, a division or multiplication and comparison. When you get to scheduling across large networks, something that is often called inter-cell interference management, or if you get to scheduling very large number of flows with different requirements, at that point one may require something other than I'm talking about here. All right. So we are basics right now. So I showed you here that if for the same example, where we got this point for maximum sum throughput scheduling and this point for proportional fair scheduling, we got this point for round robin scheduling. And if you look at many default schedulers which are available in free software or open source software, often the only thing they implement is round robin scheduling. Let us see why we get this point, whereas we got points near the boundary for the other cases. Okay. Let us see. And this is very basic stuff, but you'll see emerging from this simple example, the essence of why round robin doesn't work well. Let's suppose we have two UEs, UE0 and UE1, located at the same distance from the base station. Okay. And let's suppose that the bit rates the UEs take only two values. I'm building an example here. Let's just take two values with equal probability. The channel just takes two states. Okay. And the channel states are independent of the two UEs, which is often the assumption. So this UE0 gets a bitrate of 10 Mbps with probability half, 100 with probability half. Similarly, UE1 gets a bitrate of 10 Mbps with probability half, 100 with probability half. So in half the slots, UE0 gets 10 Mbps, and half the slots, UE0 gets 100 Mbps. Similarly here. Okay? And they're independent. It's like independent coin tosses. Now let us see what the joint channel for these two is. Okay? You can see now that with a probability of 0.25, 0.5 times 0.5, a quarter of the slots, U0 gets 10, UE1 gets 10. Right? Quarter of the time, U0 gets 10, UE1 gets 100. A quarter of the time, UE0 gets 100, UE1 gets 10. And a quarter of the time, UE0 gets 100 and UE1 gets 100. Okay? Right? Is it clear? It's like asking, that boys and girls happen with equal probability. And what's the probability that a family has two girls, two boys, girl, boy, boy, girl? Same thing. All right. So now let us look at two different kinds of scheduling, round robin scheduling and something else which I'll explain. Suppose it is round robin scheduling. What does UE0 get? What round robin means is I don't look at the channel. I simply blindly go on doing alternation. So suppose that the scheduler finds the channel in this state with a probability of 0.25. Okay. And since we are scheduling either one with probability 0.5, I will get 10 Mbps. I will get for this UV 10 Mbps. And it's 0.5 because either you get one, schedule one or schedule the other. Okay. Now, what about here? Suppose that the channel, the scheduler found the channel in this state. 10 for UE0 and 100 for UE1. Okay. What will happen? With a probability of 0.5, you schedule UE0 and you get 10. See, in any state, you keep tossing the coin, this or that. Suppose you are in this state. Let us take 100 realizations of this state, 10, 100, 10, 100, 10, 100. In half of them, you schedule UE0, you get 10. In half of them, you schedule UE1, you get 100. Okay? If you're doing it blindly. So with a probability of 0.25, you are in this row. Half the time you schedule UE0 and you get 10. What about if you are in this row? With the probability of 0.25, you are in this row. Half the time you schedule UE0 and you get 100. Similarly, in this row, with the probability of 0.25, we are there. With the probability of 0.5, we schedule UE0, they have the same rates, you get 100. So over time, you get 27.5 Mbps by doing round robin. We don't look at the channel state. In every state, we just alternate. Let us see if you do the best UE. What happens? With a probability of 0.25, you are in this state. It doesn't matter here. You will get 10, whether you schedule one or the other. What about this state? Suppose you are in this state. You schedule the best UE. You won't schedule UE0. So with 0.25, you will get 10 with probability 0. Suppose you are in this state. The probability 0.25, you are in that state. But in that state, you always schedule UE1, UE0. It is 100. Suppose you are in this state. With a probability of 0.25, then you schedule either one or the other. But then you get the same through. 38.7. Okay. So the two places where you can make a decision is in these two. Here, of course, both are 10, both are 100. Here, you schedule the best UE. Instead of just tossing a coin, in which case you sometimes get a bad channel. Here, you schedule UE with throughput of 100. Here, you schedule UE with throughput of 100. Okay. So by taking care of the channel condition also in the scheduling, you are able to improve the throughput at almost 30%, 25%. Okay. So this is why the scheduling that I showed you earlier, some throughput scheduling, maximum sum throughput scheduling, proportional fair scheduling, they're called opportunistic scheduling. They don't just toss a coin across the UEs, they take an opportunity when they get it. They see that this UE is getting a good channel, this UE is getting a bad throughput. I use that information in my scheduling. So round robin scheduling can be very bad. Okay. So round robin does not utilize the information about the MCSs available in the two UEs, thereby losing opportunities to get higher throughput. Okay. So here, the throughut pair is going to be 27.5, 27.5. Here it will be 38.75, 48.7. Okay. Now, I told you earlier that the way we choose the alpha the way we choose the averaging window affects the way the evolution of the scheduler will happen. Let us see. So here we are doing proportional fair scheduling. We've already shown you this number. Let me go back and look at it. I think it's the same example. So the number is 60. I think it's a different example here. So yeah, we'll go back there. Yeah, this is a different example. Okay. So the proportional fair throughput in this example was, let us see, 100 and, by the way, ignore the vertical, this second y-axis, it'll come later. Okay. So the proportional fair throughput, it turns out here was 110 Mbps for the red UE and 170 Mbps for the black UE. Okay. The algorithm, whether you use alpha equal to 0.405, a window of 20,000, whether you use an alpha of 0.0005, which is a window of 2,000, whether you use an alpha of 0.005, which is a window of 200, converges to the right answer, 170, 110, 170, 110. You know, around 170 to around 110. Okay, all converge. Look at the behavior. When you take a large history, convergence is slow, you know, in a leisurely manner. You can see that the number of slots I've taken is all 10 to the power 100,000, 1 lakh slots, 1 lakh slots. So it's the same time duration. When the history is large, in a leisurely manner, we converge and we take almost like 80,000 slots to get near to the money. Similarly here. You can see the implication of that. If the UE moves, it's going to take a lot of time for you to converge to the current optimum rate. Okay, if something comes in the way, if a truck comes in the way, there's somebody on the road, a big truck comes in the way and base station is there, it'll take some time to converge to the rate required for that car. Take alpha, but look at it, the convergence is very smooth. The final value is very close to the desired value. There's no fluctuation around the actual throughput. Look what happens at 0.000. Convergence is very fast. You rapidly go to the final value, rapidly converge to the final. They all start at the same point. They all start at 200. Okay, but in steady state there is a noise. Okay, that's why you remember there's a point on the curve, but the point that you see is fluctuating around the point in the curve. It's not exactly at the point. If you use this algorithm, you would be bang at the point of the curve after a long time. If you use this algorithm with alpha equal to 0.0005, you will fluctuate around the point of the curve. The fluctuation is going to be small. Take alpha equal to 0.005. Fluctuations are large. Fluctuations are almost like 20 Mbps. 20 Mbps variation in the UE's throughput around the desired rate. Similarly here. Okay. Where do you want to operate? It depends upon the mobility of the user. You know, if you have people driving, going in a 200 kilometers per hour, now much more bullet train, maybe you want to do something like this. I don't know. Okay. But anyway, this is telling you the choice of alpha. The alpha given by the by 3GPP in the 5QI tables is 0.0005. Because in the 5QI table, if you remember, there was a column, this is averaging window, 2000. That translates into a 0.0005. So for small alpha, convergence is low, steady state noise is low, and vice versa. Very long averaging windows, small alpha, can lead to longer periods during which the UE is not scheduled properly. One more thing, another thing I forgot. See, if the window is large, you are achieving the throughput over a large window. There's more opportunity for the scheduler to not schedule you. Okay? Because I want 170 Mbps over this large window. I can give you 200 Mbps now. I can give you 340 Mbps now and nothing for some time. 340 Mbps now and nothing for some time. Because I'm averaging over a long window. You're allowed to do that. But if you're averaging over a short window, then you have to give me 340 Mbps over that time and even a small throughput over that time. So a large window leaves open the possibility of a user not being scheduled for long or getting a low throughput for long. Okay. So if you're running a real-time application, it requires, if you're running, say, a YouTube video is something that's buffered. It's buffered. So I don't really care about real time. But if I'm watching the video, I need 1.7 Mbps for HD video. If I don't give any throughput for 10,000, 5,000 slots, then there will be starvation. The buffer will drain out. I require more buffering in that case. Anyway, just to give you an idea of the trade-offs here based upon choosing alpha. So ignore the right axis, we'll come to it later. Now, if you look at the industry documents, okay, and yes, yes. This alpha is a parameter of proportional fair scheduling, not of it's a parameter of EWMA, not proportional fair scheduling. So any algorithm that you have, whether it is maximum sum rate scheduling, weighted scheduling, proportional fair scheduling, all will suffer the same thing. Convergence will be slower for a very small alpha, so steady state noise will be smaller. This is a property of EWMA, you're right. Now, if you look at some documents, particularly from the industry, you will find that proportional fair scheduling is represented in a different way. It's represented as geometric mean of throughputs. Proportional fair scheduling, the way I described, the utility is given as log of the throughput of user 1, log of the throughput of user 2, summed all the way up to n. But look at geometric mean. You all know about arithmetic mean. Geometric mean is also something you may have seen before. If you have n numbers, geometric mean is just this, multiply them, take the nth root. That's geometric mean. Okay? Suppose that I use this as a measure of my network's performance. I take all throughputs, theta 1, theta 2, theta m, multiply them, take the nth root. And I use that as my measure of performance. Okay? And suppose I want to maximize that. Now, all of you should know that if you want to maximize something, if you take a increasing function of what you want to maximize and you maximize it, it's still the same thing. Okay? Because this function is increasing. So if you order something, if you order the outputs remain ordered. So if you take log of x and log of y, if y is more than x, log of y is also more than log of x. So the log is an increasing function. Let's take logs then. Instead of optimizing the geometric mean of throughputs, I'll optimize the log of the geometric mean. Let's see what happens. You take a log, you take 1 over n, log theta 1, log theta 2, log theta n. Simple. 1 over n is a constant, doesn't really matter, throw it away, and we're back to proportional fair scheduling. So maximizing the geometric mean of throughputs is equivalent to maximizing the summation of logs. Okay? So proportional fair scheduling is equivalent to geometric mean scheduling. But there's one advantage. I often tell my lab people to do the following. Do proportional fair scheduling, but report the geometric mean. Why is that? Geometric mean has units of megabits per second. It is something which is more intuitive for me. If you report to me sum of logs, I do not know how to convert logs to throughputs. So I will optimize logs. I will run proportional fair scheduler, but I will ask them to report the geometric mean of the throughputs you get, answer the MBPS. I can compare to throughputs easily, visually. Okay. So, all right. Then there's arithmetic mean throughput. Arithmetic mean is the same as, so 1 over n just goes away, 1 over n is a constant. It's the same as maximum sum through. So the important point to appreciate is that geometric mean can play a useful role in scheduling from the point of view of representing your output. Now, in the last lecture, I mentioned something about losses. Okay? When you send the transport block may not succeed. Now, I know in particular for the OAI, which is the open source OpenAI code, it tends to fill the entire transport block with one code block group, with one code block. So you just send the entire thing back. Okay? In any case, if the transport block is lost, you require some transmissions. Transport block is in error, you don't get the full throughput out of it. Even if it is multiple code blocks, the receiver will collect some code blocks and keep it. Other code blocks have to be resent. So you have not got the full throughput. But if you go back to my earlier slides for today, what do? I take the MCS. I hope you remember. I take the MCS. I convert the MCS into a bits per slot. By multiplying the MCS, by obtaining the bits per symbol, multiplying by the symbols. And then in the EWA formula, I put that entire amount into the update. Assuming that whatever I send gets successful. That doesn't happen in practice. In practice, when you send something, it can get lost. When it is lost, that's lost throughput. You thought it is succeeded, but it didn't succeed. So this is something that we have introduced. From my knowledge of the literature, there isn't much that's available, which shows you how to modify proportional fair scheduling to take care of losses. It's still work in progress, but I'll show you what some interesting stuff from you. All right, let's see what happens. In somewhat more detail, I already spent some time on it. So this is your slots. This is the data that we have. All the throughputs we got so far, all the MCSs we got so far. If there was no transport block waiting to be retransmitted, I'm assuming that the entire transport block is one port block, we reset the entire transport block. If there was no transport block waiting to be retransmitted, this is a scheduling opportunity. And then we do our proportional fair scheduling. We compute the number of bits per slot for this user, obtain the throughput from this array, divide and schedule. But they are supposed to be scheduled. Suppose this is an opportunity to schedule. We schedule. But it turned out that the transport block is in error. Transport block will have to be rescheduled later. So we reschedule it later, after some time. This throughput that we thought we got is actually not obtained, it's lost throughput. Again, we schedule this later. We thought it's lost throughput. So it will be wrong for me to compute things the way I have shown you how to compute. That's the way it is done. All right. Along with this, there is this MCS update process which goes on. Now, the MCS update process that I'm familiar with, apparently every company will, we have a delegate here from Samsung. Every company will do it their own way. The way the OAI code, which I'm familiar with, the way it updates the MCS is the following. There's a block error rate threshold. The block is a transport block error rate threshold, say 0.1. Every 200 slots, over 200 slots, you measure the block error rate. Okay? If the block error rate exceeds a certain block error rate threshold, you decrease the MCS by one step. And if you are below the block error rate threshold, you increase the MCS. If you stay below, you keep the MCS the way it is. So there's some mechanism for updating the MCS, which runs in parallel. Okay. So it is for that reason that I was saying MCS is not a constant number. The MCS is constantly being updated depending upon the experience that the UE has, the scheduler has in sending data for the UE and that MCS. MCS could go up, MCS could come down depending upon the block error rate achieved in comparison with the block error rate threshold. Okay, so this is something I've already gone through before. The way the OAI code is written, when you send a transport block, it includes that transport block as a success in the EWMA calculation. But when it resends it, it doesn't include that. It says it's 0. Okay. So it takes care of whatever error it made, takes care of it later.
Yes, the other is reduce the layering.
Yes, yes. Okay, I don't know the answer. Maybe you might be able to get the answer. But let me give you my answer and then we'll hear from the industry person. What I would probably do is the MCS is adapted every 200 slots. I'll probably reduce the layering and then I'll wait for the MCS to be adapted. But you can go ahead and sorry?
Like.
Yes, yes.
In this case, the problem with this is that why it doesn't follow in my specifications is that the first we have to figure out where the UE is looking from. When it's transmitting back to our responding to the CSI channel state information, whether it is looking at the SSP or whether it's looking at the CSIRS and especially CSIRS IM. Based on that, we take a call whether the RI that the LI information, the line rank indicator and the layer indicator information that has we have arrived on conclude that whether it's authentic or not. We first go for the layer. If the layer is not suitable, then we move to the M6. The problem here is that from release 17 onwards, we have to puncture URLC traffic in a millisecond.
Oh, yes, yes.
Because that EMBB traffic goes in this sort of problem.
Sorry?
EMBB traffic. Because we have punctured the
Yes, yes.
But EMBB, we get a NAC.
You get
Start getting a NAC.
You can start getting a yes,
So
yes.
it seems that it goes for a while period, it goes for a while.
Yes.
So
Okay.
we have a mechanism that could continue to block while it starting point. And that is the logic that you can ask. That's a good right solution.
Okay. So what he has said in a few sentences is a lot of things. I'm sure all of you know the 5G triangle. EMBB, MMTC, and URL, other way around. So the bottom left is MMTC, the bottom right is URL. So whatever. Now, URLLC is ultra reliable, low latency communication. By the way, what do they use URLLC for in practice?
So India has used for example, Samsung Galaxy Watch. It has a if it is putting a child, you know,
Child safe.
child. So we know that if the child is away from the parents, immediately.
Okay.
We know that from the one of the first time of the blood pressure, the Samsung, we know that whether this parent is wearing the watch or the child is wearing it. Now, if you have activated a link between the watch and the child runs away from the father, parent watch immediately gets activated and
Although half millisecond is rather short. Anyway, so URLC, LLC is used for ultra reliable low latency communication. And I'll talk about scheduling for low latency applications. But I'll assume that the delays can multiples of 0.5 milliseconds. What Mr. Anshuman Bose is telling us is something which was introduced maybe release 17. How many years back was that? How many years back was that? No, how many years back was that? 19, okay, quite some time, 6 years. So what it allows you to do is to break up a slot, 0.5 millisecond slot into mini slots. And if a URLC packet arrives within a mini slot, then you schedule it immediately. But at the beginning of the slot, you already scheduled a EMBB frame. So the way they do it is they actually take away some resource from the EMBB frame. It's already been coded, okay? And you stuff into that URLC bits. It's like an error for the EMBB, like having some bits corrupted. And what he's saying is that because of introducing URLC packets into a coded EMBB slot, you get packet loss, a code block loss, and that causes this problem. Okay, so it doesn't fully answer your question, but partly what he said was that the MIMO layering is reduced after that. But we can look it up and come back to you later. Okay. So for those who are not in the room, the question that one of the delegates here asked was that when there is transport block loss, do you first reduce the layering or do you first reduce the MCS? Okay. All right. Now, just a reminder, what are classical gradient scheduling? Sorry, okay, I've used a word which is new. Let me explain the word in a few seconds. So proportional fairness, you already understand that. There is an MCS. I'm using some new notation now. Let me explain that. Mu I K is the MCS that is given to a user I in slot K. And Ri mu I K is the rate corresponding to the MCS. So MCS could be 17. Ri mu I K is 17 look up the table, find the number of bits per symbol, multiply it by the number of symbols in your transport block. That's what it is. So just a more complicated notation. And theta ik is the throughput already obtained so far, and mu ik is the MCS. Okay. So what does the scheduler do? The scheduler takes the current rate as before, nothing new here, divide by the throughput and do the maximum. This algorithm, by the way, belongs to a class of general algorithms called gradient scheduling. Why is it called gradient scheduling? If you take the derivative of log, you get 1 over x. Log x derivative is 1 over x. This 1 over theta actually is coming from there. The general scheduler is you take the gradient of the utility at the current rate and multiply it by the rate you get in the current slip. That will give you 1 over theta times Ri. Let's leave that aside. It's just a term for a class of scheduling problems, scheduling algorithms. And then you update the EWMA. Okay. Now the question is, can we incorporate the fact that you can use data in proportional fair scheduling? Okay. So the usual proportional fair scheduler does not account for transport block losses. So I give it a name. I call it proportional fair loss unadaptive. It doesn't care for loss adaptation. It will do the same thing. You see, the proportional fair scheduler does the same thing whether or not you're going to have a loss. You don't account for the fact that you could have a loss in your system. Would it not be more reasonable that given the history of loss that is taking place for this particular MCS for this UE, I modify the R by accounting for the possibility of loss when I send the grade. Let us see how we can do that. So I'm going to introduce to you a class of loss adaptive schedulers. Okay. And what is this? What the base station now maintains is something more. There's, like they say, there's no free lunch. You have to pay something to get something. Let us suppose, in addition to the throughputs that the base station is maintaining, all those theta bars that the base station is maintaining, and of course the MCS that the base station has, let's suppose the base station maintains one more thing. It maintains for each UE and for each MCS a matrix of the number of reattempts made for that UE, for that MCS. So now it's a matrix. Suppose you take UE 10. There are 30 MCSs. For each UE, you maintain a matrix. If I use MCS 17, this is the loss rate I get. If I use MCS 10, this is the loss rate I get. I keep this matrix. 100 UEs, I require 100 by 30 matrix. That may or may not be practical, but let's leave that aside. So I maintain some more data. I keep a history of the impact of using a particular MCS. Okay? And then I modify the proportional fair scheduling in the following way. If I cover this, let's cover this for a second. Cover this. This is your classical proportional fair scheduler. You take the current rate and divide by the throughput. What I do is I subtract from this rate the throughput that I have got so far, multiplied by the corresponding element in that matrix. Okay, so I'm scheduling UEI. UEI has MCS mu I. This is the rate the UEI will get with MCS mu I. This is the usual way of getting the spectral efficiency multiplying by the symbols. I look up the matrix. This is the loss rate I get for using that MCS for UEI. So I have now reduced the throughput, the rate I would get from that particular MCS by a number. Why does that number come? I'll spend a couple of slides on that a little later. That number comes for the following reasons. Okay, this is a heuristic. Simple heuristics, what I do is R, I'm using the rate R. If I have an reattempt rate of say 0.1, that means I require one reattempt per 10 attempts. I divide R by 1.1. Thereby reducing R a little bit. And now I compare the UEs. This is approximate. This is the actual correct algorithm. Why do I do this? I do this for the following reason. It actually comes out of the EWMA algorithm. Let me explain that. Okay, so there are two ways. I'll show you some results. There are two ways of modifying the rate I'm getting in a slot to account for the fact that I could lose data. I reduce the rate, and then I compare the UEs. All right. Here is, okay, I'll skip this. This is a little technical. I'll skip this. Okay. Now let me show you the consequence of that. If I use the proportional fair scheduler and there is losses taking place in the network, I get this rate region. If I use the modified scheduler, I get this rate region. This may look small, but actually this corresponds to 1.5 dB increase in SNR. People who work in actual systems know 1 dB is a lot of improvement. We're able to get 1 dB improvement simply by a scheduler accounting for the fact that there's losses taking place. Whether or not this can be implemented in practice is something for practitioners to say. One thing more I would like to say here, the scheduler, you can do suboptimal scheduling, you can do optimal scheduling. If you take a suboptimal scheduler and obtain for that the rate region by doing all those tangent planes and all that and get the rate region, you will actually get a smaller rate region. The rate region is here obtained by an optimal scheduler. Okay. So just to indicate that if you do not account for losses in the proportional fair scheduling, you can actually lose 1 to 2 dB of performance. Okay. Maybe. Well, let me quickly give you an idea of why that correction is done that way. Let me show you what happens. And I'm going to show you something to create an image in your mind, and then we leave it at that. Let's suppose this is a scheduling opportunity. Okay, these are slots. Scheduling opportunity. My reattempt queue is empty. It's a chance for me to schedule data for some UE. I schedule data based upon some algorithm. It will be proportional fair algorithm. Schedule the data. X means the data is lost. I should reattempt. Now let's assume that the time that it takes for me to get the information back from the UE is 0. I'm taking a simplification. I immediately know after I send the data that this packet has been lost. I reattempt immediately. Just giving you a conceptual idea. Reattempt immediately. I reattempt immediately. Finally, I succeed. So we have made 4 attempts to send one successful transport block. Next time, so now the transmission queue is empty, the reattempt queue is empty. I again schedule. In this case, there were 4 failures and then a success. This is highly exaggerated. Typically, you will have 1 failure occasionally, but just to explain that. Now, suppose I do EWMA, what happens? If I do EWMA, I should really do EWMA between here and here. Okay? Because when I account for the throughput I get, I should account for the throughput I get over this time. I get throughput only over that time, right? I don't get throughput right away. I was able to send 1 packet successfully over 4 slots. Here I could send 1 packet successfully over 5 slots. So this term in EWMA, see, theta k plus 1 is the old theta k plus some 0.00 something minus theta k. This term has to account for the fact that for some time I got no throughput. Okay, that is exactly the kind of term that I showed you earlier. So I won't go into this. So it is R minus something, R minus some loss of throughput because of not being able to get success for 3 slots. Okay, so the EWMA calculation over those times when you are getting packets successfully is the reason for that. It is not this. This is the default proportional fair EWMA, where what you send is what you get. The corrected way of doing EWMA is where you discount for what is lost. I'll leave this aside, and I think today, this is my last slide for today, a little ahead of time, ask some questions. Okay, so in any scheduling problem, there is a constraint. You have a network, you have some propagation phenomena, you have some powers, you have some distances. That sets what you can do, the rate region. Okay. and you have some objective. I want to maximize utility. Okay? So if you're given all the constraints, you're given the entire constraint set, you're given the objective function, you can optimize that offline using optimization calculator. But we don't have that in practice. So we have to implement online learning algorithms. These algorithms collect data and they online learn the optimum point. So from the MCS values achieved over the TTIs, the algorithm learn the desired operating point depending on the objective. The rate region is in the data. The rate region is not given to us. It's in the data. Okay. We never stop and first discover the rate region and then schedule. We don't do that. We just begin the schedule from time 0. And the algorithm should be such, it puts you in the right point eventually. Okay. The learning approach is classical. Neural networks and this approach began around the same time. This has been around and successful for a long time. Neural networks have become popular, useful only in the last 10 years. And we are hearing from the industry that now they're becoming used also for scheduling. I'll look it up and come back hopefully next time. Okay. So, and in neural networks, this has become useful. This has become implemented for about 25 years. And I've given you a summary of it. A summary of the lecture so far. We learned about the QoS requirements, the 5QI table, the architecture for 5G quality of service. We learned about how you pack data, IP packets into the 5G NR OFDMA grid. We learned about the throughput region and its properties, convexity, quality convexity. We learned about optimization for various objectives on the boundary. And then we learned about scheduling algorithms and MATLAB code and demonstrations. Introduced some loss adaptive scheduling. And in the next class, I will begin to talk about some extensions of all of this. I'll talk about scheduling the rate guarantees to begin with. Then I'll talk about network slicing and some examples. And then finally, I'll get to scheduling for real time, maybe towards the end of next lecture. So I'll stop now. It's 12:50. We can spend some time on questions if there are any, either from people here or from the remote audience. Thank you. Any questions? Anything, either from here or from outside the I can be around in 10 minutes. You can ask questions offline. Yeah. But okay, from my understanding, scheduling is not during the station. The downlink scheduling is done in the base station. Sorry, yeah. And the uplink scheduling is also done in the base station. The UE keeps sending what is called BSRs, buffer status reports. And the buffer status reports go to the base station. So there's some delay. So the information available to the base station is a bit outdated. But as far as I know, that's how scheduling is done. Maybe you can correct me if I'm wrong. Yeah, so
It moves from backend to participant.
when you move from?
Backend to participant.
Oh, okay. Yeah. So what's the question? I thought you said scheduling is done in the UE. So I misunderstood you, huh? Yes. Okay. Yeah, okay. Now I understand the question. The assumption in everything I've told you is that there is one DRB per UE, and every UE has a full buffer DRB. Okay. Now suppose you have two DRBs in this UE, and two DRBs and one DRB and three DRBs. Then you can design scheduling. I'll talk about some of the scheduling, which is where some buffers are full buffers, some buffers are real-time buffers. We'll talk about that next time.
Say it's not CP.
No, you don't prioritize. You see, strict prioritization. So what is prioritization? Prioritization is like you are a VIP. Your car can go first. That's not the way networks should work. I mean, of course, URLLC is one example of strict prioritization. The moment the packet comes, you send it. Okay. But the best approach, okay, let me pull back a little. Most applications, and even I think even this child safety application, applications have some deadline. Okay. I can wait, the robot can be in the state that it is desired to be. It'll keep moving in the right direction for 20 milliseconds. The dynamics is such, if you control it once in 20 milliseconds, it requires one more control 20 milliseconds later. 20 milliseconds is your is a target. By the way, I'll go back to one slide to get out of this. Just to give you a flavor of the answer I'm giving. I had it in the beginning and let me show you this slide. Can you see the slide? So if you look at this slide, you'll get an idea of a practical application and what has been defined by 3GPP for this application. So this is mobile robot, controlling of mobile robots. Let's take one of these. Let's take this, for example, this first line. What does it say? I want a system reliability of 99.99, 6 nines. 10 years time to mean time between failures. My message sizes are 40 to 50 bytes, say 250 bytes. Okay. And the packets are coming, say, every 20 milliseconds. Survival time is the transfer interval. That means if I get a packet, the packet can go back. If I have to send a packet to the UE, and the packets are coming 20 milliseconds apart, it can reach the UE 20 milliseconds. That's enough. So there will be a requirement for a particular service. It can be a hard deadline, it can be a probabilistic deadline with a probability of 0.99, deliver it. So prioritization is not the right way of doing it because you have many activities going on. And you have to schedule all the activities, each.
Fine, never
thing
হয়ে গেছে কারণ
has
থ্যাংক ইউ সো
objective.
মাচ এবারে আমার 2 মিনিট লাগবে স্টপ করতে
So just forcing a packet to go immediately, even though it can wait for 20 milliseconds, is not the right thing to do. But maybe URLLC applications are such that it will require immediate require. I do not know what the applications are. I think child safety also can wait 20 milliseconds. PU, video, yeah.
So at M3, the M3 itself, so the entire video, especially used for XR applications. If the entire video has a latency and everything impact equals, comes to the MAC layer. If we can schedule it, we can get it that scheduling, you don't take off get that.
Drop it, yes. You drop it, yes. So if the dropping is such that it meets your probability of violation, suppose that 20 milliseconds is the is the deadline. And suppose that the application can be satisfied with the deadline being met with a probability of 0.99. What percent of the package can drop? Okay. Drop because of errors, drop because of violating the deadline. That's the design of the scheduler block. Okay, I think we can stop now.